The next speech is also reserved for the gold partners of this year's conference, EPAM Systems. Our next speaker would be Vladimir Ageev, lead data scientist at EPAM Systems, who unveils the journey of transforming tables into answers with his talk, From Tables to Answers, Building Q&A System for In-Document Searches. Vladimir, an expert in personalized recommendation systems and natural language processing, will present on tabular Q&A in unstructured PDF documents. He will cover the entire process, from data preparation to model development, offering valuable insights from his team's experience. Join us for this enlightening session on combining tabular data with Q&A systems. Vladimir, please welcome to the stage.
So, hello everyone. Thank you for joining. Let me just check the clicker. Okay, it works. So I'm Vladimir. I'm a lead data scientist at EPAM, and today I'm going to talk about tabular QA application in document search for our product. It will be a rather technical session, sort of a case study, and we will cover different aspects of that project. We will start with a business problem. I will talk about our product and what's the feature is. We will cover some models which are state-of-the-art in this problem. And then we will go on fine-tuning one of those models. And I will talk about what kind of data we prepared for that, what kind of metrics we achieved, and how the whole process was organized. And after that, I will cover some pieces of our production system. So let's start with the product itself and why do we might need such a feature in it. So the product we are working with, it's a system which provides access to very technical documents to engineers. And the goal of this system is to enhance their workflows, meaning that they can use knowledge from those documents in their engineering work. Again, so we are providing millions of very specific, very technical documents and enhance access to them with different ML-powered features like search, comparison of the document, extraction of entities, and linking on those entities. So tabular question answering is just another feature in that set, which might help engineers to get more than they interact with documents. So what we found is that we have like hundreds of thousands of documents which contain tabular data, and what is important here is that it's numeric data, meaning that traditional approaches like keyword-based search might not let users find that information in the document because they might not know the exact name of parameter or exact name of table. And deep learning models that are usually used in that field, including large language models, are really good at working with text data. They are really good at highlighting pieces of text that are related to the query or generating that answer, but they are not that capable of capturing structural information like tables and working with numeric data if we need aggregations of that data, for example. So, more formally, if we assume that we can extract tables from the documents, we know how to do that. We also have a retrieval engine for that, so we can search through the tables. Our task would be, given a query, highlight cells in the table, or give an aggregation over those cells. So even more formally, as our input, we can expect a structured representation of a table, like JSON here, with texts of cells and their coordinates in the table. And as an output, we expect to have, again, text of our answer, along with coordinates of that answer in our table, and along with some operations over those cells. So let's now move on to the models which are capable of solving that task. So if you're going to Google tabular question answering or similar things, you probably end up on Papers with Code or similar website with a list of models and data sets and their scores. So here we have a plot with scores on the Wikitable questions data set and quite a few models in the list. So first of all, we can see here that even the most powerful, most capable models achieve about 60 to 65% in accuracy on that data set. And most of them are fine-tuned on the training part of the data set, meaning that if you are going to apply them to your specific data in different domain or in different structure, you will probably get even lower scores. So SOTA for today, according to Papers with Code, is data. It's a model. It's a system that uses OpenAI API under the hood, and it doesn't suit us because we do not find that secure enough. We also have a tabular model in the list, which doesn't have a license that allows us to use it commercially, so we also skip that. Other two models are OmniTab and TabX. Those are both sequence-to-sequence BART-based models, which means that they generate answers, and we need to do something else on top of that generation in order to highlight our cells and to figure out what operations were done by the model in case we need that. So our choice fell on TAPAS model. It's a simpler model, which is not the very best on this data set, but it's very understandable. It suits our needs in terms of it can highlight cells and classify aggregations, and it has a nice license which allows us to use it in production, in commercial system. So if we look closer at this model, it's a transformer. It's a BERT-based model, so it's transformer encoder, but with two classification heads, which means it can, again, classify cells as answers and classify operations like averaging, summation, production, or counting the rows. And also, it's capable of capturing structure of the table using different types of positional embeddings for column IDs, rows IDs. It also can try at least to capture the difference between comparable data in the table and just text, for example. And of course, it differentiates between query and the table as an input. So we selected our model to go on. And now let's go into fine-tuning. But first, we would like to define what would we like our system to answer. So what kind of questions it should be capable of handling. So we have different types of those. First of them is extractive type. And it's a simple type of questions which, as an answer, there would be just a cell highlighted or multiple cells highlighted in the PDF in the table. Another type of questions is generative, meaning that we not only would like to have an array of cells selected and highlighted, but we also might want to have an operation over them, again, some averaging, counting, and so on. And finally, we would like our system to be able to differentiate between questions it has information to answer to and questions it doesn't have enough information in the table to provide an answer. So here, for example, we have a question on Mistral model, which is not presented in the table. So our system shouldn't output any answer. No highlighted cells, no operations. So for this case, we annotated about 30,000 of examples, about 3,000 of tables, and 10 question answering pairs per table. And it took, for a rather small, but I would say a team of subject matter experts to annotate it, it took about 3 months, which is quite a long time. And it turned out that this task is very complex to actually formulate, to define what should be the correct answer, what type of questions we can ask in that settings, and so on. And another thing here is that we did that in several rounds because we wanted to have, from one side, a very diverse set of tables with different structures from different documents. And from the other hand, we would like to have multiple tables from the same document in order to measure things like retrieval quality or just have scores at document level. So let's imagine we started our fine-tuning. How do we evaluate performance of a model like that? Of course, we can start with classical metrics like F-score. And we did that. We applied it over sets of cells and a set of text of tokens. And of course, we can average them over different slices of data, like at question type slice, or over table, or over document, or over the whole corpus. But as I mentioned earlier, those models are achieve about 60 to 65% in accuracy, right? So is it enough to actually have it as a feature in our product? What we did to confirm that is we ran an impression test where we had basically a test group of users who used the prototype, and they were answering questions about quality of those answers, about quality of retrieval, and like general feeling about the feature itself. Is it very poor performance, or is it very good? So another thing to note here before we go to the metrics and some other details is some tricks we used and that worked for us. As for resources, it was enough for us to have a single A100 GPU from NVIDIA. We did a couple of tricks to speed up training, like gradient checkpointing or using mixed precision matrix multiplication. We also did some tricks around optimization of learning rate and around our data, because we found out that on some types of questions we got overfitting. So we wanted to undersample those examples in our batches during training. So now let's look at the performance. We fine-tuned 2 types of tapas model, tapas large and tapas base. So in red, you can see here the large version of it, fine-tuned one. And as you can see, it performs the best. On the other hand, we have this blue line here, which is base model, which we also fine-tuned. And here you can see that scores are pretty similar to the large one, but this model is 2 times smaller and faster, so we went on with that one. It also can be seen from the table that our scores on our custom data are twice as high as pre-trained model, the model from the papers with code plot, right? And another thing noted here is that our generative capabilities degraded strongly on our data set, probably because we didn't have enough annotations of operations. So I think the question everyone has when they start to work with NLP problem is, can we use LLM for it? So a good prompt should solve all of our problems in all NLP tasks today. So we tried exactly that with an open source Llama 2 model. And we faced all the common issues of those models, like hallucination, with model providing answer outside of context of the table, with difficulties of understanding exact coordinates in the table, and finally, just providing us structured output that can be automatically parsed and used in other systems. More specifically, we tried Llama 2 70 billion one LHF fine-tuned. It was quantized, so it's fit in our A100 GPU. And as you can see here, it has scores which are a bit better than Tapas base model, which means that today you can have an open source LLM which outperforms your pre-trained, not fine-tuned model with zero-shot prompting, right? But still, this model doesn't perform as well as our fine-tuned version. And another thing to note here is performance. In our experiments, Llama 2 on GPU was about 5 to 10 times slower than Tapas on CPU. And today, you can actually remove that gap in latency with things like VLLM. So the speeds are actually can be comparable. That's achievable. But still, you will be comparing GPU price versus CPU price, and Tapas model can be, or BERT models in general, can be optimized as well for inference. So most likely, you will pay more for an LLM running on your GPU. So we select our model, we fine-tuned it, but again, the best score we've got in our tables previously is about 60%. So is it enough, again, for us to go into production with such feature? So what we noticed is that during the impression test is that retrieval is like 80% of success here. So if a person just sees the table, of course, they can come up with a correct answer from the table, especially in case of documents with a small amount of tables or just small tables. So we come up with the idea that we would differentiate between complex answers, complex questions, which we are not sure without model. We're not sure that our model can perform well on those, and simple questions. But here we can't rely on Tapas, actually, because it doesn't provide like a good distribution of confidence scores or probabilities. So it just outputs zeros or ones. So for that, we had built a binary classifier. It's LGBM-based pipeline, which uses query features, table features, and features from Tapas itself in order to classify questions to simple or hard. And again, hard questions are just highlighting the table. And for simple questions, we highlighting the answer in the table or give a result of aggregation. And this binary classifier works rather well. And for selected answers as simple, we are sure that we are getting good enough answers, and overall scores of those are good. So finally, I will cover some aspects of predictionalization. Here is our pipeline, and I will go over some key components of that pipeline step by step. So when in the beginning of the talk, I told that we are assuming that we can extract tables, retrieve them, decompose them. So for that, we have a custom-built OCR engine, which has a tesseract inside of it, but also additional components for layout decomposition, meaning that it can extract section names, it can extract titles of the document, different paragraphs, and like the whole hierarchy of the document. And what's important for us is that it can extract figures and tables for us to use. Another component is search itself. So we have a search index where we store our tables along with their features used for classifier. And we also have an Elastic-based service plus our custom Go-based services. Their goal is to provide an API for ML engineers in order to create basically search pipelines, manage collections, and so on. So for us, it gives an opportunity to bring our custom model into general search pipeline, which is used across the whole product. So finally, our model was wrapped as an MLflow model and deployed as a REST service as part of the search pipeline. And answers from this model were shown on the UI for users as the search answers. So if we are going to summarize the talk, what our experience showed is that tabular question answering in general in this natural language setup doesn't seem to be solved yet, even with LLMs. So you might need some data to fine-tune on. And again, it turned out for very specific, very, how to say that, parameter-rich tables, it might be quite long to annotate such data set, especially with small group. And here you need subject matter experts to do that. So it might take quite some time. But that's worth the wait. So in the end, it can boost your performance up to twice, in our case. And this is something that might be used in production system. And finally, note on evaluation. So we are usually trying to use both offline and online types of evaluation. In perfect scenario, you would want to do an A/B test over that feature. But if you can just have a focus group, people trying your application, that also will give you a lot of information and feedback on how your raw metrics, like your F-scores, translate into actually usefulness of this feature in your product. And this means that sometimes small accuracies like ours is good enough for this feature to be in the product. So thank you for being with me through this rather technical talk. Here are the links to my contacts and my colleague who did a lot of experiments during that project. So thank you a lot.
Let's see if there are any questions. Or was this too technical for us? Here.
First of all, a great presentation, great topic. I have a question about LLMs. In your presentation, you used only Llama 70 billion. But did you try some smaller, let's say Llama 2, model 7 billion and 30 billion? Because it is shown that those models, those sizes, are often enough for a small amount of tasks. And it's also possible to fine-tune them on one GPU.
Yeah, I totally agree. In that project, we didn't try smaller LLMs extensively. But in others, we can see that using LoRa, for example, for fine-tuning, you can achieve really good performance, even for smaller models. And yeah, so if you would like to have a setup where you have, for example, an LLM for multiple tasks, actually, this is probably the preferred way to have a single LLM and fine-tune it on different types of tasks. So yeah, I think in the next couple of months or years, we will get there. But today, my message was that those specified models are more easier to fine-tune, and they are faster.
Yes, they
so
are, yes.
Probably you will choose those as your productions.
Thank you.
Yeah, thank you for the question.
Hi.
Hi.
How do you tackle the problem of indexing tables? Do you embed them, and how?
No, we actually do not embed the tables. So it's the index I showed here is not a vector index. We basically store them as like JSON structures, and we have first stage retrieval in our search system, which does basically keyword search. So it outputs our candidate tables for a query, and then we apply our question answering model to actually answer those questions. So the like semantic search with embeddings would be also applicable here, but we just find that this setup works good enough for us. And you actually can use tapas to generate those embeddings because it's trained on that task as well.
Thank you.
Okay. Any more? If that is all, then... Okay, we have a question there.
Yeah, thank you so much for the presentation. I just have one question. Have you considered these tasks not as a like full ML or end-to-end ML task, but with an ML part and some deterministic part? What I mean, just having a tool to extract table, its structure, and like a tool that helps to understand the query, can we convert this task to a regular tabular, like relational, maybe table task and solve using the existing tools? What like objectives and performance issues maybe have you seen there?
Yeah, I totally agree with you. In like perfect scenario, we could indeed like somehow transform query to a SQL query basically, and have those tables stored in some database. But in our case, those tables are stored in the PDFs. And sorry for clicking too much. So basically, this OCR process is not perfect. So we do not get a perfect structure on the of the table, actually. So this is why we would like to have something more robust to text representations, let's say, to work over the representation we get from our PDFs. So if in case that OCR and table decomposition is perfectly solved, this would be the better way, I think, to have it in SQL.
Thank you. If there are no more questions, Vladimir, thank you very much for this presentation. I'm giving you a certificate as a lecturer at the DSC, and we have to thank Vladimir once again, please.
Thank you. Thanks a lot.
Thank you. Thank you.